Right. Hello, everybody. It's time to deep dive on data again. I'm Jason Hunter, a principal solution architect focused on DynamoDB, and I'm here with some guests from the OpenSearch team. Let me start with John. John, could you introduce yourself?
Sure, I'm John Handler. I'm a senior principal specialist solutions architect, and I focus on Amazon OpenSearch service, the open source OpenSearch project, and indeed all of our search technologies.
Awesome. And also Hajar. Hajar, could you
Hi,
introduce yourself?
everyone. I'm Hajar Bouafif. I am a senior analytics solutions architect focusing on OpenSearch service.
And today the goal is to talk about search, how we find things, and there's a whole bunch of different ways. You think it's easy. I think search is easy. I go to a text box and I type in a thing and you give me what I want. This can't be hard.
That's the magic. That's the magic,
Right?
Jason. And we are today going to peel apart the curtains and look at who's running the show.
Apparently there's some magic that happens between me typing a phrase and you giving me exactly what I was looking for.
Yeah,
So today we're going to like keyword and lexical and vector and neural sparse and RAG. There's a whole bunch of different keywords. And I'm going to learn along with you if you're in the audience. You know, these two are going to educate me and show me how the stuff actually works. So let's see. Let's start with what is OpenSearch exactly? You both work on OpenSearch.
yeah, sure. So OpenSearch is a search engine. I think we're all pretty familiar with search experience. I go to Amazon.com. I want to buy a product. I have a little window. I can type some words, and Amazon hopefully then goes and interprets those words and brings me back the product that I was looking for.
Right.
And you know, it's a very textural thing. There are some UI elements called facets that enable you to set filters and drill in and provide additional information about the search. But fundamentally, you know, what a search engine does is it matches the words that you type with words in the product, in its description and its title, in the brands and other attributes that are part of that product, right? So the search process is really about taking words and matching them to words in a catalog of products, or at least it was until maybe 10 or 15 years ago.
So OpenSearch does this for us.
Correct.
Like I load things. It's like a database?
Yeah, it's like a database. Search engines do sit in the databases world, so it's a very familiar kind of from the back end interaction where I load in my data as what we call documents. Documents are just structured blobs of JSON with you know, sort of fields with name of the thing or description of the thing or what have you. OpenSearch then indexes everything and makes it searchable. And then on the query side, you just send in a query. OpenSearch retrieves you documents that hopefully match that query.
Let's never say blobs of JSON again.
Fair enough.
I'm not sure I like this terminology
into a search
we're going down. I mean, it reminds me of, if you're old enough, card catalogs where you do OpenSearch manually by pulling out, you find an author name, and on the little card it would say like, it's in this shelf, it's in that shelf. So you just took physical card catalogs and did it, right? Was that like the first search engine was like index catalogs?
Well, sort of. I mean, so you bring up card catalogs, and it's funny, many of the folks may not have ever seen a card catalog.
Yeah, these days.
Used to be, you went to the library and there was a card, you know, a big piece of furniture that had hundreds of thousands of little cards, and you'd go and read the card, and they were organized by like subject matter, by author, by what have you, right? Not the first time that we've ever tried to organize information. In fact, you can go way back in history to ancient Sumer, where when they were creating the tax rolls and they were, you know, stamping in the cuneiform in the tablets, they actually made tablets that indexed what was in the tax form tablets, right? All the way through Greece, where in the Library of Alexandria, there were scrolls that were lists of or indexes of what other scrolls were in the library. Through modern library science, which is the kind of card catalog that we were talking about. So people have been organizing and finding information forever. And it's a very kind of, you know, meaning-driven process, right? So until until recent times, it was that word to word. But of course, the word-to-word matching can be somewhat unsatisfying. My favorite example, if I want to buy an 8-foot blue couch, I can go to Amazon, I can type 8-foot blue couch, and Amazon will return to me a long list of 8-foot blue couches, right? But if I want a cozy place to curl up by the fire and read a book, I can't go to Amazon and type cozy place to curl up by the fire and read a book, because the words cozy place, fire, all of that wouldn't match any of the couches that Amazon knows about. And so the revolution that we're seeing, and I'm sure everybody in the audience has heard about Gen AI and has heard about sort of vectors and Chat GPT, and we've come to this point where we're able to get at the meaning of what I mean when I type cozy place to curl up by the fire, so that the search engine can then match my meaning rather than the words that I type. And that's
All
what
right, I think
we're gonna look at
that's
today.
what we're gonna get to.
Yeah, exactly.
Everything these days has semantic meaning to it. All right, let's start with, well, cuneiform. Should we start with, what's the queries per second they could achieve with that? Was that
Yeah,
Sumerians as a service?
the bureaucrats had to shuffle through all of the clay tiles, and so it was a very slow. I think their query per second was about 1/1000th, right, of a
They made a
query.
bunch of copies though, so they scaled out. They had read
Yeah,
read
exactly.
shards. Oh, shards with tablets. They were shards.
Yeah, there you go.
All right. So let's start at the basic stuff. Like because I think when I do a search on my file system and I'm looking for a file name or something, that's very exact, right? So how
Correct.
does that work? Let's not get into like cozy fireplaces yet. I just met you.
Okay.
Let's start with that. How does that work at a technical
Sure.
level?
Say again the query. It just flew out
But
of my brain.
anything like a file name contains, or a
Okay,
file name
sure,
equals, or something like a
sure.
file system search.
Let's say I have a file called 8-foot blue couch, just for fun.
Okay.
So as the application developer or somebody who is building search on top of, let's say this is some kind of data lake in Amazon S3, I am going to, as the application builder, walk the S3 bucket and then look at the file names of everything and probably pull in the metadata as well to construct a JSON document out of that, right? And
Okay.
so I'll have one of the keys in my JSON document. It'll be a dictionary. One of my keys will be file name. And then
Okay.
I will have 8-foot blue couch, however I spelled it, as a file name. I'll send that off to OpenSearch.
Okay.
OpenSearch will take that field and do what's called text analysis. So it will parse the field to split up the words 8 and foot and blue and couch and make them all matchable. OpenSearch, like many search engines, works with what we call an inverted index. Inverted index takes all of the words 8-foot blue couch, puts them in an index, and then that index points to what are called posting lists, the lists of all of the documents that contain each of those terms.
It's like the
So
card catalog. The little card contains a list of places, and then I look up 4 different
not exactly.
cards.
I'd say more like the index of a book, right? If in the index of a book, I have a map from words to pages. In the index of a search engine, I have a map from words to the JSON documents that have those words in them.
And the question is going to be, remember, and if I misspell it, where FT foot is a good example, or feet.
Correct.
Whatever.
Correct.
That's a whole other challenge. But at this point, we've still spelled it correctly because we're figuring out how
Right.
to
But
find
to
it.
respond to the question, like sometimes I misspell things, there are ways that search engines have developed to deal with things like misspellings. So in the analysis of 8-foot blue couch, that piece of text, right? Or in the query, I can apply fuzziness that allows edits, if you were. It's Levenstein distance. I don't know if anybody knows what that is.
Yeah.
But
How
it
many
allows
character
how many character
mismatches we have.
differences. Yes, exactly. So that's one way to deal with misspellings. Another way is I can bring in synonyms. Synonyms enable me to add multiple words that all should match the same thing. And I can deal with some misspellings that way.
Common
Let
misspellings.
me just close the loop on the query,
Right.
on the 8-foot blue couch, right? So now I have an index and it's 8 points at the 5,700 documents that contain the word 8. and foot points at the 12,000 documents that say foot, etc. Right? As a query comes in, I apply the same kind of parsing. So if I query for blue couch, then I'll parse the query to be blue and couch, and then I'll go look up blue and I'll look up couch in the index. That gives me two sets. The sets are the posting list, the list of documents that contain those terms. I then do a set intersection to find everything that is blue and couch. That gives me a list of matches. Now OpenSearch is going to apply a scoring function to decide which is the best match. And we won't get into depth about that, but the idea of the scoring function is to say, well, blue is a pretty common term and couch is a pretty rare term, let's say. And so blue gets a pretty low score as a single term match and couch gets a pretty high score. I look at each document and the score for that document is the number of times that each of those words occurs times the value of that word. Right.
So I'll get a hit for this is a really blue couch.
That would actually pump up your relevance. Yes.
And now we've done SEO already.
Yeah.
We're 10 minutes in and we're SEO optimizing. This blue couch is really cozy by the fire. All right, Hasher, you've got a demo of this, right?
I do. I do.
Let's throw up a demo and make it. I mean, I think we've seen search, but let's see OpenSearch do search.
Yeah. All right, so in this web application, we'll run some sample queries today to demonstrate the different type of search that we can run with OpenSearch. And we'll start with the basic lexical search that John has been explaining. Let's start with a query looking for a 1080 pixels touchscreen camera and run the lexical search using this query. The data set that we are using in this use case is retail data set that has different items regarding footwears, clothes, electronics, etc.
Okay.
Let's run the search. Here we expose 5 results from the query run.
You can probably move that StreamYard thing.
Yeah, I'm seeing a little kind of window there or something. Yeah, let's move that all the way out of the way. Yeah, there you go.
Is it good now?
Yeah, it's good.
Awesome. All right. So let's check the results. Here, the highlighted terms with the color orange are the exact match between the input text, which is the query here, and the terms within the document. And that's basically how the lexical search works. It will match what you have in the query with what you have within the document data set. So here we have a match with 1080 pixels for HD. We have a match with camera, touch screen, the same for the others. And looks like lexical search works miracles here.
It's got a grep. I mean, for nerds, this is fancy grep. It's 3 greps, glue it together, there's your hits. You understand why it's a hit, put it in orange.
Yeah.
You said this word, this one has this word. Maybe you do a little bit of fuzziness, cameras.
Yeah.
Right? That's stemming.
That is stemming. So, this is exactly, of course, illustrating how the word-to-word matching works, right? So you're seeing the query 1080p touchscreen camera. We're seeing where all of those things match. This is the kind of query that works pretty well. This is like the 8-foot blue couch query, right? Because most of the descriptions of these results contain those words. And so when I match, it's actually matching what I intended when I said 1080p touchscreen camera, right?
Yeah.
Should we try with another query?
Should we do a cozy, something like that?
I don't think it's in there.
Cozy,
so I think we understand this one, right? Because this is just as a nerd, I kind of like this. It's like don't interpret what I mean. I mean this. I want to match this, right? And it's very literal. There's very little magic. Yes. But especially, I think the more casual, the more you're going to type your intent in there, the less it's going to work because your intent and the keywords may not match up. What's an example of that you could do, Hatcher?
Here, the good thing is that we have exact matching terms between the query and the documents. The challenge starts when you don't have the match, right? let's try with another query here. I will look for 42-inch LED TV.
Okay. You should
Using
try
the
OLED
same
sometime. It's
lexical
much
search.
better. But yeah, fine. All right, what do we get?
All right, what do we have? So we have a match with LED TV. We still have a match with LED TV in these use cases, not exactly 42 inches.
It says TV
We have a
close
match with
enough.
TV.
It's an LED bulb.
So,
All right.
now, what do we have here? We have a
Red
lamp
shoes.
and shoes. And why would you have these results? This is because
It has inch in it.
exactly. So for the lamp, we have the LED match between the tokens in the documents and the token within the query. And for the other one, we have inches. Basically, it's not highlighted, but it's here somewhere. 2-inch, 5-inch, black.
So, this happens all the time, right? You go to the search engine, you type some words, you get some results, and some of them are kind of okay and it's kind of close. And then you have to go think about what, and rewrite your query in order to try to match the thing that that you mean. But the search engine is only matching words, so it's not actually coming with the thing that you mean, right? And so there's this iterative process we've all trained ourselves up to go and iterate through one-shot matching. Okay, well, LED TV, 42-inch LED TV wasn't a good match. Maybe I'll add some more words here, and that'll make it match better.
All right, so Colleen's jumping into vector search. She knows the solution. Let's talk about the solution here. Back to John. So
sure.
when I want intent, I use vectors. What's a vector? What
Sure.
Like, how long ago was this? 10 years, 15 years ago, something like that?
Something like that. Yes, this technology has actually grown out of stuff that was going on in the 90s with neural networks and a bunch of stuff like that.
Okay.
So what is a vector, right?
Right.
A vector is a quantity with a magnitude and a direction. That's its definition. In practical terms, a vector is a big array of a lot of floating point numbers, right? And each of the slots in the array, if you will, is one dimension in a multidimensional space. So if I have the vector 6, 4, right? So it's just two integers, and 6 would be my value on the x-axis, and 4 would be my value on the y-axis, right? That gives me a magnitude. If I take the distance formula, it gives me a magnitude, and there's a direction, there's an angle with respect to the axis, right? So that's a two-dimensional vector. Now, when we use vector embeddings for search engines, these are much larger. These are typically 384, 768, a lot more dimensions than that. So that's what a vector is. It's just a bunch of floating point numbers that specify a location in a multidimensional space, All
right. So a bunch of numbers, a bunch of floating points. I don't know why they didn't do 1,000. Like, let's do 784.
Okay, sure.
People are weird. They just like the power of 2 more. There must be a reason. So I have a bunch of floating point numbers, and that defines like the meaning of a document in some multi-dimensional space.
Yeah, so the advances in natural language and sort of what we've done with transformer models in machine learning, right, is to create a kind of model that is able to train on textual data initially. Like it works with text and audio and video. You can push all kinds of data into one of these models. The model learns a function that maps the text on the input side to one of these vectors. You train it on incredibly large amounts of data, the whole web, right?
Okay.
And what the model learns is how to project points into that space where the correlation between words is close to the same, right? So semantically related similar things end up at similar locations in that multidimensional space.
The document is the thing that ends up at that space point?
So the chunk of text, whatever, if it's a single word, If it's a lot of words,
Okay.
you push it into the model, and the model produces one of these vectors, which is, again, a point in the space where related stuff is close together.
So as puny humans, we picture a 2D as, you know, a graph, a 3D is space, but then you're going to give me almost 1,000 multi-dimensional space,
Yes.
which is where all concepts live. And
Yep.
in there, this chunk of text has a conceptual point, which is what it's about, which, you know, it's kind of like our brains work, like cow milk kind of thing, right? We're like, what do cows drink? Milk. No, water, right? Like they
Right.
tricked your vector in your brain to say the wrong thing. And so then I can take all of my data now, instead of thinking of it as words, I think of it as points in a multidimensional space.
Right.
And now you're going to do a query for Cozy by the Fire, and you're going to make that into its own multidimensional point. There is a point in the universe that is you sitting by a cozy fire.
Not exactly. So, and I do want to respond to Sharp Pixel just quickly. So Sharp Pixel, OpenSearch is, OpenSearch service is an AWS service that provides the core OpenSearch project wrapped in a bunch of AWS technology to make it simpler to run in the AWS cloud. So yes, in a sense, you can use OpenSearch to add website search functionality. You would run OpenSearch, and then you need a crawler to crawl your web pages and push them into OpenSearch. So I wanted to respond to that question.
Yeah, it's oftentimes used for like catalog data where you own the proprietary JSON format more than like an HTML thing.
Yeah. So coming back to your point, you said milk cow, and those are related because if you think about all of the sentences in the universe that have ever been written about cows, many of them will have milk, right?
Okay.
And so what the model learns is that correlation between terms, and it has an attentional mechanism that helps it look at a particular term and what surrounds in order, again, to learn how to produce a vector that's at a particular point in that very large space, right? Okay. So there's not per se John sitting on a couch by a blue couch by a fire, because probably there's not many things that have been written or we would train a model on or could have trained a model on that are about me, right? Some stuff is out there.
The transcript of this show is going onto the internet.
Well, there you go. So there will be something that where the correlation, John, and so somehow in some world that the point for this show will make me drift closer to blue couches and fires.
All right, so I load my data. Every one of them gets a vector description of it conceptually. Now, when it's time to do a search, how do I glue the two together?
Yeah, so you then, once you have your catalog of data, and by the way, there's a lot of really interesting stuff that goes on about how you pick the piece of text that is representing the particular document. If we think about the LED TVs, I could pick the name, I could pick a description. There's a lot of text associated with that particular TV. And so what you choose to use as text to create the vector that describes that TV is a whole process and a science, right? If you think about it, if I have a 400-page book and I pass all 400 pages in, it's not going to really capture, like, the meaning there is so dispersed and so broad, it's not going to capture that meaning. Okay, so the mechanics, let's go back to, so you have to cut it up and you send in paragraphs, right? Because meaning is kind of local to that paragraph. Just to answer the practical of your question, and so we can get on to the demo, I've created now vectors for each of my products in my catalog. I take the query and I use the same model to produce a vector for the query. I then look at the distance of the points in my catalog for all of my products, and I compare how far away is the query from all of those points. And that gives me a score. That's how I rank and find related things.
Distance and multi-dimensional space.
Correct. And there are a lot of
You
distance
say
measures.
that like it's so easy. Like, of course.
Well, of course. Well, it's, there's Euclidean distance where you just take the square root of the squares of the differences, right? So it's a very simple
Okay.
distance
That's like
measure.
how it, if I was going to shoot you in a three-dimensional space, it's the shortest distance to shoot you.
Correct. That's right.
Right.
There's a cosine distance, which measures the cosine between the angles of the two vectors. That's a little bit harder to understand. There's a Manhattan distance, which is
Me
go
shooting
block
both
by
of you.
block.
How far I have to move my gun if I'm going to shoot both points? I got this.
There you go.
What else you got?
Yeah,
What's the
Manhattan
other way?
distance. If I were walking on a square grid, how many steps would I have to take to go between them? So there are a lot of different
Okay.
ways to measure distance, but the key
All right.
concept is things are related by, the closer things are, the more related they are.
Okay. In multidimensional space. All right.
Yeah.
So I take your query. It's a multidimensional point. I have documents that have multidimensional points, and I say, find me things that are nearby in concept space.
Yep.
All right. How's your prove it works?
All right.
I'm skeptical.
All right, you shouldn't. Okay, so let's try with the same query with the 42-inch LED TV. You remember the search results with the lexical search?
Right. I got
with the lamp and the
stilettos,
shoes.
right? Yeah.
All right. Now let's try the same query with the vector search. So as
Okay.
John explained, we already generated the embeddings for the documents that we have. In this use case, we generate embeddings for the image description. And we'll also generate an embedding for the query and compare the embedding of the query with the embedding of the document. So
Okay.
this is what will be done now once I click on search. We'll learn that similarity search between the two embedding vectors. All right, let's check the results now. So it looks like
So for no shoes, that's good.
we don't have we don't have the same concept of term matching here anymore. It's not about term matching; it's about context matching. So even if we don't have the 42 inches, we understand the vector search understand that you are looking for TVs, LED televisions, LED TV, and it will provide you with the items that will match that intention, that will match the same context without exactly matching terms. So here there is no highlight, there is no exact matching with 42-inch, for example. We have some LED TV, but overall it's about context understanding. If I try with
the no highlight, like you could have highlighted though, like you could have found it by semantics and then still highlighted. If the number 42 is there, you probably could have lit it up.
Yeah, I'll try with another query. Trendy footwear for women.
Footwear for women.
So here we don't specify any type of shoes or anything, and we'll see what are the results that have been produced here. So
yeah, there's not even the word footwear in there, is there?
So we have some matching with footwear. Women by stylish, for example. We have style, we have comfort. Here there is no footwear mentioning. There is no term footwear. However, we have sandals. We have some women matching. For this one, for example, we have sleek black heels or type of shoes, but no mention of footwear. There is no mention of women either.
Right.
And even if we don't have that term matching, we understand the term context. And this is what makes the vector search powerful and helps to overcome some challenges with the lexical search.
Yeah, that's crazy. There's a question here on searching neighbors in a space without walls. Sounds philosophical, yeah. What do you think of a graph database? Could I do a graph database since we're kind of talking about space?
So thank you, SharpPixel, for the question. That's one of the methods. So when we look at how does this all work in a search engine itself, right? And what kind of queries do we run? You could actually take the query vector and compare with every single vector for every single document. That's called exact nearest neighbor. That's not very performant. If I have a billion documents, I can't do I could, but it's too slow, right, to do the distance calculation for all of them. So we
right.
have some approximate nearest neighbor algorithms that in different ways, two algorithms in different ways that build a local neighborhood so that I don't have to explore so far in the space. And one of
Right.
those is called Hidden Navigable Small Worlds, HNSW. And HNSW actually does build graphs of the space. So it takes the points, it finds neighbors, and it builds graphs at progressively deepening levels of granularity. So I start with a very coarse graph, which I traverse to find myself close enough. I drop down to a finer granularity. I traverse a graph to get closer, finer granularity, etc. So there are graph ways, and there are ways of reducing the amount of work that you do by employing graphs. The other one is called inverted file IVF. What that does is it uses a clustering algorithm to find clusters of points, which it represents as a centroid for that cluster of points, and then it finds the nearest centroid to search that smaller neighborhood.
So
Jason, we lost your audio. No, we cannot hear you. Okay, still can't hear you, Jason. Maybe Hajar, you want to quick
Yeah.
dive into this.
Yeah, let me give an example, John, of what you said about the HNSW and the embeddings itself. So quickly showing you an example of a document that we have in the data set here. So within the document data, we have some metadata regarding the color of the item, caption, the description of that specific image, and we also store the embeddings of the image, right? So here we have three types of embedding that you can see, multimodal embedding that we'll check later, description embedding, bedrock text. And this is an example of how an dense embedding vector looks like. So I think you explained well this part, John. Now, in order to generate this embedding, what we are using is a feature called ingest pipeline in OpenSearch. And this ingest pipeline will use a processor.
Let me just pause for one
Yeah.
second, Hajar,
Right.
and just to orient folks and let them know what we're looking at. So OpenSearch comes with a UI layer called OpenSearch Dashboards. OpenSearch Dashboards has this administrative interface where you can simply type HTTP requests and send them directly to the OpenSearch cluster in the background. It's also a tool that enables you to build visualizations and dashboards on top of log data, but we're primarily looking at search. In the left side, you can see the actual command that Hajar is executing, and on the right side, you get the search engine's response to that command. So which was the query that we were looking at? Is it this match all query?
Yeah, I gave an example of the document structure, and this, yeah, Jason is here. Hi again, Jason.
what did I miss?
I can hear you.
What did I miss? How far? I feel like it was just getting to the critical juncture. What are we looking at?
Jason, was it something I said?
I know, right? Something Bluetooth said.
Yeah, so we explained the document structure, what you have in terms of data. We have the usual metadata that we see in lexical search, for example, and the documents that you may have within your data set, whether retail data set, healthcare, etc. So you usually have a list of attributes that presents metadata related to your items. In this use case, we also add the embedding of the document. Here we are generating the embedding for the image description. And this is how a vector embedding looks like. So a list of numbers, float numbers that will represent that vector in the high dimensional space.
Isn't that crazy that defines semantics?
It is.
That just a bunch of numbers
just
is
a bunch
meaningful.
of numbers.
It's just like whoever first did this was like, yeah, look at this. These numbers work. All
right. And here,
I feel like we should plug the survey right around now, right?
Sure. We can plug the survey now. We can plug the survey at the end as well.
That's we're about halfway done. I want to make sure that people know that there's a this is the URL can put up on a slide.
Yeah, let me share the URL.
Here's a tiny URL. You can do that. Might be easier.
So that one, you have it?
You had it and then it went away.
It's coming in the...
We prepared
I'm
a
seeing
few
the
slides
fastest
for you,
slideshow ever.
just in case.
We did have
Just
some
in
slides,
case.
but honestly, we really wanted
This is the one.
to talk with you all rather than
Sure.
just spend a lot of time in slides.
Yeah.
So.
All right. So if you're one of the first 50 people to do this, $20 credit. Pulse.aws/promotion/capitals PZ2CR3. That's a letter O, N, like it ends on. So I'm going to make sure to do that. Now,
Is it clear?
I think so. For the next thing I want to get into is, I'm old school. I like searching exact. Some people like to be like gesture in the general vicinity. Can you make us both happy? Can I do like
funny you
exact
should
Panasonic
ask.
thing and also LED TV? Can it work both?
Funny you should ask. Yes.
Mm-hmm.
So there's something called hybrid search. So as Hajar showed you, we have some metadata in there that we potentially want to match, like a color. We just want to match the color, or if I'm looking for a specific part number to fix my sink, I want to match that part number exactly, right? We also have vectors for all of these documents. So OpenSearch has a plugin called the Neural plugin that makes this kind of hybrid searching simpler to do, right? So it enables you to send both a text query and a vector query, and then it's able to take the scoring from the lexical and the scoring from the vector, normalize to put them on a similar scale, and then apply an averaging or apply different kinds of averaging to bring a combined score that is both lexical and vector.
So if I don't know which type of person you are. I don't know if you're the type of person to type a Panasonic part number, or the type of person to say a quiet dishwasher. In which case quiet needs to have a semantic meaning or whatever. And so you can do both at the same time, and then you get the results, and then you kind of interleave them according to relevance somehow. Normalized relevance, I believe you called it, right?
Yeah, you normalize the scores and then you compute an average. And this gives you, in some ways, the best of both worlds, right? It enables you to both have that lexical and also the vector match.
I guess it's just a little more computationally expensive. I have to do both.
It is a little bit more computationally expensive. Yes.
Hajar, you're going to show it to us?
Of course. Okay.
Of course.
So,
of course.
we have all type of search in this demo, so good thing. Let's try with the query that is similar to what we offered earlier. 1080 pixel touchscreen camera, but we're adding for beginners.
Yeah.
If I run the lexical search using this query, we'll have, as usual, the exact matching between terms. However, there is no exact matching for the beginner. Right. So nothing related to beginner level. It's mostly pro level performance, video needs. So in terms of a user, or if myself as a user, okay, I have the 1080 pixel touchscreen camera. However, I might not be reassured that I will be able to use it because I'm still starting or beginning with the photography, right? Now, if I run the same query using vector search, vector search, as explained, will not have the exact matching, but will have the context matching. Okay.
Yeah, that's not a 1080p camera.
It's not. Yeah, exactly. So we have the matching. We have the matching of the level, so it is easy, it is quick. Professional quality photos, on the fly, effortless. So we understood the intention of the user that we are looking for easy to use camera, but we don't have the exact matching. Here we have one, but it's not an exact match with the term as within the lexical search. Okay, so we have the lexical search that does the exact tokens matching, and here we have the context matching. And this is
Right.
now, if we take the best of both worlds and combine the vector search and keyword search results, let's see what we'll get here. So we start to get the exact matching. So here are some items that have been already actually provided by the keyword search with the exact matching: 1080 pixels, 1080 pixel camera, etc. But we'll also have other items that do not have that exact matching, but will also provide me with the ease of use. Simple, anywhere, anytime. Provides versatility for audio photography needs. So it's not only related to the exact matching of the pixels quality. And we can even fine tune this by giving more value, or what you call weight, to each subquery. So in this use case, for example, we are giving 50-50 to vector search and lexical search or keyword search. We can change that and saying, I would like to prioritize the results from the lexical search. And here we give more value to the keyword search, more weight, to have more results basically coming from the lexical search with some flexibility using the vector search. And if we run the...
This is because OpenSearch is this hugely capable. This is one web interface that you built on top of OpenSearch, right? At the back end, you can ask OpenSearch to do this, weighted this, relevance, that, right? So it's not like this out of the box is all that you get with OpenSearch.
Yeah. Let me jump into how this is done in hybrid search. So we have the same document structure as we explained later with the embedding fields and the metadata fields. Right. So, and this is the index mapping. So we have the list of metadata. We have the embedding fields type, set, ASCII, and vector type. And for the hybrid search, as explained by John, within OpenSearch in itself, you can build the normalization process to normalize the scoring from the lexical search and the vector search, because the outcome is different. It's not on the same scale. So you need some normalization process. If we didn't have this feature in OpenSearch, you would do that normalization outside of OpenSearch in your application, basically.
Slower, probably that way. Yeah. Praveen asks, can I tell the difference when I'm scoring him? Can I determine whether a specific result came from a vector search or lexical search?
Yeah, so you see it in the results, right? So with the highlights, for example, you see how much results you get, or the ways that you, based on the ways that you provide, you can understand the results scoring from which type of search are you getting them, basically.
Yeah, this is like in the open source project, we don't internally, OpenSearch does not expose the individual scores. That is, in the open source project, we have we're working towards bringing those scores and making them so that you can do more specific things just with the scoring and building scoring functions. But for the present, the scores themselves are not exposed. Like as Hajar said, like you can see from the highlighting kind of what's matching in terms of the lexical, and you can tweak the ratios. So
no.
And here we use this processor, or like a search pipeline processor, to build this normalization process. So here we are using technique, like we have different techniques that you can leverage. Here we are doing the min max for normalization and arithmetic mean between the scoring within each type of subqueries. And here the weights that we defined earlier, 70 and 30%. And when you'd like to run the search query, you would need to call that search pipeline that we defined here with the processor within your search query, okay? And in the search query here, you will list the subqueries under the hybrid query. So we have the lexical query here, and we have the neural vector search query here.
All right, I want to switch gears a little bit, because there's another way to do the semantic search besides these big, long float numbers, right? Something sparse.
Oh,
I think it's sparse.
Yeah, right. So Sparse vectors.
Before you go there, what if what is relevant to me is actually not less relevant to the search engine? Well, that's the lesson of the world, isn't it? I need to scroll through results for the engine to understand what's relevant to me. I guess that's a personalization question.
Yeah, sharp pixel. So vector embeddings is one in the set of tools that search technology has evolved to kind of answer the thing that you're saying, right? Because for a long time we've been trying to bring the relevant results. It's super important. If I'm running like an e-commerce site, bringing a relevant results means that my user is going to buy that product. Obviously matters a lot to me. So personalization is one way that search engines and actually search systems, really, because the search engine itself is just doing the matching and scoring. There's a whole other universe of information about how people interact with the website. Again, just taking e-commerce as an example, what brands of shoes I've purchased should actually feed into how the application or how the website writes the query that includes that brand preference, right?
Right.
And so
your location, who you are,
correct.
all the stuff feeds in.
Yeah. Correct. So
that makes it.
The search engine itself provides the tools to adjust relevance based on your personal preferences. The application employs those tools and does the tracking about what you as an individual have done with that website before.
All right. So let's talk sparse, because the one vector search, a lot of floats, but there was something sparse. What does sparse mean? What is a sparse vector?
Sure. So the simplest way to say it is a sparse vector is a vector where you have where you have a set of tokens that is a reduced set from the original vocabulary. I start in my product catalog, I have 10 million words that are potential tokens to match. In sparse vectors, those are funneled down into about 30,000 pseudo tokens, and the same kind of learning process that enables an LLM to generate a vector embedding generates weights for that set of 30,000 tokens. And so when I take my document, I get similarly, we're in a multi-dimensional space with about 30,000 dimensions, and where the points are kind of labeled, you could think of it, with these pseudo tokens, right? So in the same way I take my document, I code it with a sparse vector, and that sparse vector gives me a location in the space. I take my query, I code it as a sparse vector, that gives me a point in the space. Now, for the query, we're able to use those pseudo tokens and match them as if they were tokens, and then use the weights of the vectors to do a dot product for the score. This will probably make more sense if we just look at one of these sparse vectors.
I'm thinking so. Why would I do this? How's bring it up? Tell me, John, why I do this.
Yeah, well, so because you're retaining some remnant of all of the tokens that you started with, right? It retains some of the character of token to token matching. And that gives me a different cut at sort of this hybrid idea, right? Also, these sparse vectors are much smaller in terms of memory consumption and much faster in terms of latency to process. So I save cost and I reduce the latency of doing the actual searching.
So it's like the semantic vector search that we just talked about, but lower cost, faster, as kind of another vector way to go. You sold me. All right, Hajar, what do we have here?
Okay, let's try with the query think backpack, and we'll run a keyword search. So we'll always compare with lexical search to understand the difference in results here. So Bing backpack, we have few matching results. Then we have non-relevant results, completely non-relevant results. We have match with pink, but this is a shirt, and here we have flowers. Now, I think you understood the vector search, right? Concept. Now we'll try with the sparse search, and we'll see the compare the difference here. First, let's look at the results. So we have pink backpack, pink backpack. Well, we have pink. It's not a backpack. This is a handbag. but the context is
Close.
dissimilar. We are looking for bags.
Right.
So we don't have that full non-relevant results. This is actually providing more options for your user to rethink their queries, or tell them that even if we don't have enough items for you here, for the backpack item, we still have other pink type of bags. And how this works. So as John explained, if we take this document example, this image with the caption, we expand the caption of the image using a list of tokens and the associated weights of a token. Here we are using a machine learning model called encoding sparse models. We have Splade that is like pioneer in the sparse encoding space. OpenSearch also released open source pre-trained sparse models that will help you generate this sparse vector. And this type of enrichment will help capture the context of the documents and match it with the context of the query. We do the same for the query here. So you see the expanded query. We have pink, we have backpack, we have bag, we have coral, that's similar to pink, we have dress even. And this is just this is not the exhaustive list of tokens, right? So we are taking sample just for the demo here.
This is very understandable as a person versus almost 1,000 floating point numbers in a multidimensional space. This is like your queries kind of like these words, the products kind of like these words, and then you kind of go back to keyword searching, don't you? That's why it's lower cost and easier, right, John? Like you just kind of like, hey, your words here, your words there, these sort of match up, and I'm not doing.
You're not doing a complex multi-dimensional vector distance calculation. You're doing a dot product calculation between a short, a set of 30,000 long, but mostly zero vectors, right?
Right. Semantics can work across languages. What about sparse?
Yeah, I'm not totally sure about that. There's no reason it shouldn't. You'd have to train the model on multiple languages. I don't know how well it would work, and I don't know if anybody's tried that. There are multilingual LLMs that create embeddings out of multiple languages. I don't know that anybody's done it with sparse.
Right. Shall we have a few minutes left. Should we talk multimodal?
Yeah, let's talk multimodal. And I'll do the extremely brief way of saying it is words are one way of providing what I mean when I'm searching. But as we all know, picture is worth 1,000 words. So wouldn't it be cool if I could use a picture also to help specify what I'm searching for, right? So a multimodal search uses text and images and sends them to an LLM that can deal with both of those. And then the query includes both a text and an image. Let's see how that works.
Okay, let me share my screen. Okay, so I selected multimodal search type here. And now we'll we'll use the trendy footwear for women as a text input. For the multimodal search, you can search using text only, image only, or both text and image for more flexibilities for your users to search what they are looking for. Here you can upload an image, but to make it more fun, I will generate an image here and we'll look for beach sandals. And we'll give it a search.
So you're querying text and image, and to do the image, you're just going to Gen AI an image?
Yes.
You don't want to upload from your file system. You're like, just make a...
This is a gift for you, James. Like, I know you like cool stuff, so let's do cool stuff.
All right.
All right, so we have
those are fake images of sandals. All right, fine. So imagine that I took this picture. Fine.
Which one, Jason?
Hey, yeah, the left one. I liked the yellow and the red. It's very snazzy. It's very trendy footwear for me.
Okay, so we'll use the both text here, trendy footwear for women, and the image that you selected to search. So we have both here as an input.
It's not very bright and yellow and red.
And now
you did find the sand. Like they're all sandally, right? even if they're
Not
not yellow and red.
necessarily. Not
There may not be some in the catalog that's bright yellow and red. That does have a unique look.
not necessarily. So here we have actually, if we look at the results, they're all summer footwears, even though I did not specify this in the input text. Earlier, we've seen some type of shoes that are not summer shoes, they're not sandals. Here we see all summer shoes, the same style with the straps as well.
Do a black image, like make it, do a color with the photo, like black shoes or something, and see if we can get the results to be everything black without actually using the word black in the query. Let that, keep that, no, not up there. You got in the text image.
Yeah.
The text should be trendy, but the image should be black.
Right, so keep the same text query.
Actually, what happens, let me explain. So what happens in multimodal search is that you will generate an image using the style that you are looking for, and then you can add more metadata using the text. So here you will say, for example, beach sandals, but I would like them to have black color, for example, in text input. That's usually how it is done, or like provides better user experience. But here, just for the
Maybe
example that you're looking
sneakers instead of, I don't think there are going to be black beach sandals, right?
Just do some black shoes.
Yeah.
Yeah, that works. Like sneakers. Has to gen it.
Yeah. Okay, this takes some time. I may probably should have cleared the results first. Okay, we have some results.
Trendy footwear, black, pick one, go. You've got 1 minute to get me my shoes. Let's see if this is going to be trendy black footwear.
Okay, so we have the two images, the sneaker and the text. Now
look at that, it's black, and you didn't say the word black because it looked at the picture to know it was black.
Correct.
So it looked at the picture. It understood also we have women, right? Remember? So we have item for women in the black shoes, that style. We have sneakers as well. And this is based on the image form basically, type of shoes.
I mean, that's pretty cool. I can go to the catalog. I can be like, kind of like this, show a picture of a shirt or shoes. I can add a description that isn't using the words of the thing. You bring it together. You understand the semantics of the text. You understand the semantics of the shoes. Glue it together with some keyword in if you want to go hybrid, because I can go hybrid with all this stuff, weighting adjusted as I want. And now I'm going to spend all my money. We got 2 minutes, so I wanted to, we had RAG as something we were going to cover, but we didn't get to. So John, do you happen to have like a book or anything that covers any of this subject?
Well, it's funny, Jason. I wrote down a lot of what we've covered in this session, and I think we're going to be sharing a link. It's a free O'Reilly report. It is really designed to be a quick read. It's not super long, but it does cover all of the material that we covered today. I don't think we made it clear. The demo that we're looking at is not OpenSearch. That's a demo that Hajer and a colleague built on top of OpenSearch. So we've been kind of cutting back and forth between the UI and the OpenSearch dashboards. So OpenSearch itself is an open source project. Y'all can go and download and use on any kind of hardware across multiple clouds. Of course, AWS has our Amazon OpenSearch service, where, again, we run OpenSearch and manage it for you in the cloud. So I just wanted to clarify, the demo is just a demo. All of that stuff you can accomplish with OpenSearch.
All right, so this is a free book that you helped write, John. And if you want to understand everything in there that we just talked about, this goes in depth. It was about 40 pages. I joked with John that he published it in April. I'm like, it must be out of date by now.
Yeah, kind of is.
With how this stuff is moving. All right. And so with that, we'll end the show. And next week, Aditya comes back, and he's going to talk about how to upgrade Amazon Aurora MySQL from version 2 to version 3, same time next week, 10 a.m. Pacific, Thursday. As a DynamoDB person, I have to mention, if you think upgrading databases doesn't sound fun, I mean, Dynamo, you never need to upgrade anything. I'll just point it out. But if you're using MySQL there, or MySQL, you want to come to that and see how to upgrade. All right. Thanks, everybody. And thanks, John and Hajer, for everything. This was
Thanks,
really
Jason.
fun.
Thanks, Hajer.
Thank you, John.